All right, let's start it. So welcome everybody to the LeetCode study group section. This is session 4. We have my name is Karen. I'm the moderator for the section, and we have Chethana who will be the presenter and the awesome amazing content creator for this section.
Awesome.
There you go, Chethana.
Thank you so much, Karen. Welcome everybody to session 4 of the LeetCode study group, where we are tackling different kinds of patterns in LeetCode, sometimes successfully, sometimes with a lot of complications, but we're learning some things at the end. So today, this session is mainly focused on a greedy approach or greedy algorithms. It is super, how do I say this? It's got a lot of, the actual coding part will be very less, but it has like a lot of like proofs and like concepts within it to generally understand what a greedy algorithm is. And we'll do that introduction first, and then we'll do a deep dive of jump game, the problem discussion, and the test cases, and talking about the different approaches with their time complexity, and then coding out the greedy approach to the problem. And we'll also talk about next problems that we can tackle, and some Q&A at the end. Okay. 1 second. Let me just bring up my my speaker notes as well on the side, in case I don't want to miss anything. Perfect. Let's start with what the greedy algorithm is. And when I say CLRS, it's the Introduction to Algorithms book. It's like this really, really big book that a lot of us might have seen. It's got the best kinds of definitions for everything. Basically, it's like your primer to algorithms. So CLRS is the shortened name of the authors of the Introduction to Algorithms book. So I've linked that there if you want to just check out the book, or take a copy or something like that. A greedy algorithm always makes the choice that looks best at the moment. That is, it makes a locally optimal choice in the hope that this choice will lead to a globally optimal solution. Oof, okay. So a lot of words, but it does make sense, right? If you actually think about it, basically this algorithm, it will make the best optimal choice at each step of the process. And it just assumes that at the end of this process, you're gonna get like the optimal solution for the entire problem overall. So local optima, or like a locally optimal solution is that for that particular sub-problem, you take the main problem, you'll sort of break it into sub-problems, and for each sub-problem, you'll solve it optimally. And you're just going to assume that, once you solve all of these sub-problems optimally, that by induction property, it sort of means that you solve the entire problem optimally. So it's like yeah, definitely. It's one of those, but it's very difficult to come up. Like for me, I've noticed it's very, very difficult to come up with greedy approaches during like any kinds of like pressure situations, like interviews and stuff. But let's hope that we can do better after we go through it today. Perfect. We're going through a lot. So now let's talk about the two main elements of a greedy algorithm. Okay, so greedy choice, optimal substructure. Before we get into, like generally I think everybody who's solving any of these algorithms will start with that recursive kind of thinking, like, oh, like maybe I can use backtracking for this, or like maybe I could do this thing, like using dynamic programming or something like that. But like getting to the greedy part may take some time, but let's sort of dissect what these two mean. So when we say when we say greedy choice, it means like we make locally optimal greedy choices at each point to get to the solution, right? So it's like we take that one particular subproblem and then we see that it's going to, if we solve it optimally, we solve it. So how do we solve it optimally? We just, pick whatever we can do at that moment, whatever is the best in our head, or whatever is the best we see, we just pick it. And then like, that's it. Like we solve that subproblem. We do this greedy choice at each step of the problem. And then when you say like, and if you say subproblem, what I've marked with that asterisk is that in the end, by doing all of these things, by working through all these subproblems, you're eventually going to like, you're going to get to the bigger, globally optimal, like entire solution to the problem. And for each step of this process, a greedy algorithm does not look at like, it doesn't sort of like revisit its choices. It makes the choice and that's it. It just moves on. It doesn't do what backtracking or like dynamic programming and like all of those recursive algorithms do. If they see that something's wrong, they revisit and go back and change it and come back. And that may also like, in many cases is super unnecessary. And like, it's like a waste of like processing time. So might as well learn, how to make it better. So I spoke a lot about the greedy choice in many roundabout ways. So we'll talk about the optimal substructure now. A problem, I'm going to read what's on the slide because like, I feel like, this explains it the best when we actually look at it like this. So a problem is said to have an optimal substructure if the best solution we come up with to the whole problem contains within it optimal solutions to subproblems. It's sort of paraphrased from the book I was talking about before and whatever I was saying before as well. So tiny like solutions to smaller problems, optimal solutions to smaller problems will lead to an optimal solution for the whole problem. So that's how we can prove it. And greedy algorithms are very, yeah, awesome. Have the book, like definitely have it in handy, like for greedy, for backtracking, for dynamic programming, a lot of concepts actually. Thank you, Celia. Yeah, so so why are greedy algorithms or approaches super difficult? Because for each problem that you have, you need to sort of prove that your algorithm works. Okay, like you can't just, like you can't have like a template. Like if you look at 2 pointers, we had like, oh, okay, like we're gonna have like a start pointer, end pointer. We're just gonna like move things around. It's gonna be the same for all problems. If it's like a big problem, and then if it's 3-sum, 2-sum, 3-sum closest, there's so many of these problems on LeetCode, but you have a pattern there. And for this one, you sort of need to think about why you think your solution works. Many times it's very difficult to prove it, but it definitely, like, it's sort of like thinking smartly and then like just applying it. And I promise you, like as we do more and more of these problems, we'll get like a better like understanding of it. Awesome. So what is that? Okay. Now let's sort of talk about greedy choice, optimal substructure, right? So let's talk about a very, very classic kind of example. I think everybody may have like come across this before. It's called the fractional knapsack problem. You may have seen the 0-1 knapsack problem, but it's pretty similar. Both of them are super similar. So like you have a bag, okay, and you have like a capacity for the bag. Now in this case, it's 15 kgs. So you have to fill up the bag such that you sort of, okay, you have a bag, you have a bunch of items, okay, and each item it has like a weight and a value associated to it, and you have to fill up this bag with the items such that you maximize the value of the items you choose. What does that mean? Like if you have like maybe something for like here, if you have something for $10, you would, that's the greedy approach, right? You'd pick something that is worth more value. So you take that and you'd put it in. So that's what we mean by maximize. At the end, it should be the maximum. And the total weight of the items we choose, it shouldn't exceed the capacity of the bag. And I do not know why I left an underscore, or I mean a hyphen over here. I will remove that. So the total weight of the, like, you know, like the total weight that you choose, it shouldn't obviously exceed, you shouldn't be super greedy there. I mean, you can still carry things in your hand and like take everything and go, but like, yeah, let's just assume we can't do that. Okay. So what is the maximum value we get? This is basically this is the problem itself. Like, what is the maximum value you get given these constraints? And also, the only difference between a 0-1 and a fractional knapsack problem is that in a 0-1 problem, you either take the entire item or you leave it. Okay, you can't do like, suppose your weight is 15 kgs or something like that, and you somehow filled up to 13 kgs, and then you have like the only items left are like 3 kgs and like more than that, which means you can't pick them. You can't take, you know, like you can break a half of them and take it in that case. But that's the 0-1 knapsack. This is the fractional knapsack. So let's just assume that we can, you know, depending on our item, we can break it and we can like basically have it, you know, we can take whatever we want, like a fraction of whatever we want, so that it reaches the maximum capacity, also maximizes the value. I also want to quickly mention, because like for some reason, when I thought about like looking at things like finding local optima and stuff like that, I thought of an AI algorithm called hill climbing. I'm not sure if we're all familiar with it, but it definitely seemed like, you know, I for some reason I sort of thought let's also quickly mention hill climbing. So like it's one of those algorithms where you would be at this point, your ultimate goal would be to reach the top of the hill, but you have to climb it, and you have to do it in optimal ways so that you get to the top. Like, and every single time you will be at a point in the hill, like suppose you're starting maybe at the base, and from where you are, you need to calculate like your nearest neighbors, and then you would, I think there's something called the cost function that we need to minimize. I'm guessing it's minimizing, but you need to sort of choose which of the neighbors you need to go to, and then so on, you reach the top. It's sort of like it just feels like it has a greedy underlying within it, like a greedy approach underlying within it. But like, feel free to look at it if you have some time later on. It's called a hill climbing algorithm. Both, I think it's just like a greedy heuristic or something like that. But yeah, let's just go on now. So yeah, so we have this kind of problem. Now we have to see how do we do this. Okay, so because we're doing everything greedily, yeah, I'm just gonna wait for some thumbs up. I hope I didn't like, talk too much. Or awesome. Great. Love it. Okay, so let's continue. How do we solve it using this greedy approach? We talked about these two properties, greedy choice and optimal substructure. So what do like in this case, we had for each item, we had a weight and a value associated to it. Thanks, Karen. Yeah, if for some reason I just felt like it had like that thing within it, the greedy thing within it, but yeah. So we have two lists, and before I start, and I won't be completely working out this problem. I'm hoping we can do this as an exercise in the channel, and like I swear, like we need to like we'll definitely like work on it together or like something like that. But yeah, let's just discuss. Hopefully these are some good hints or stuff to get you started. But yeah, there are many solutions on the web as well for fractional knapsack. So we have two lists, weights and values, arrays, weights and values. And like obviously each index would be the item number, right? So like that part. And then how do we actually because what does this greedy choice mean? We need to somehow do some kinds of manipulation or something like that where we can make this kind of greedy choice first. So in this case, we can sort by value by weight to sort of make sure that we are like that we don't that we don't choose things that may not add value later. This particular way of sorting, this heuristic, is how generally we can start doing this problem. And then at each point we would just pick the most valuable item, and then we would add it to max val. And if we have like some kinds of like fractional fractional items or something, like if we, like I was talking about before, 13 kgs and 3 are the 3 kgs and more are the ones that's remaining, then we need to pick by fraction. So we should also make sure that we don't exceed the capacity or the limit of the bag. So so if we can't pick the entire item, we would need to pick a fraction of it, of that weight, and add the corresponding value to the fraction to max val. Seems a little bit here and there, but I think I'll also link some, Karen, if you could remind me, we could also link some solutions to this later on. Okay, didn't see the, should move the Q&A somewhere else. What am I doing? Sorry. I think I was just trying to move something around. Anyway, where were we? Okay. Sorry about this. Sometimes I get very quickly distracted. I think should change that. Okay, we're back. So this is the greedy choice part of it, where we sort and then we pick, right? And then next, what is the next thing we wanted to talk about? Being slow, but yeah, the next thing was the optimal substructure. Since we sort of sort the items in terms of value per weight for each item, then we know like we're going to pick the highest ratio there, right? Like the highest ratio of value per weight. So then we know that we're always going to pick the higher ratio. That means we're yeah, like I'm gonna quickly go through this and then look at the chat once more, because I like, yeah. So so we know that at each point we're going to pick the most optimal kind of solution, because the first item we pick will be the most valuable, because like if you sort by like value by weight, highest ratio, the pair of like weight to value, that particular item, the most valuable item will be at the start of the array, and then we'll pick that. So if we pick that, then we're just going to like the second item, that would be the first item we pick, but the second item we pick will also be the most valuable item for the remaining set of items, and the third item we pick will be the most valuable item from the remaining set of those items, and so on. So this means that at every single point you pick the most valuable item, and the most valuable item in our case is the most optimal solution. It's the locally optimal solution for every subproblem, and each subproblem is the choosing of the thing, like of the weight at that particular step. Whew, we're done with that. So because of this, by induction, since we pick, like we spoke about, since we pick the best solution at every point, then we sort of pick the best solution for the whole problem. So like, you know, like, then this means let's just go back to where is that slide again? A problem is said to have an optimal substructure if the best solution we come up with to the whole problem contains within it best optimal solutions to the subproblems. I think we sort of did that. So I think that particular, you know, part of fractional knapsack, it sort of solves the whole, like, you know, the two properties that we need for a greedy approach. And I like, you know, this works. This just works. So yeah, that's like, I'm not gonna solve this. I hope like if like it would be great if we could just solve it based on, you know, like even if you have like if you could find the maximum value based on this, the numbers we have here, and or like a code-based solution, we could do that. Like if anybody's interested, like just message on the group, and I'm sure like one of our teammates, like they'll get back to you on it. So yeah, where were we? Great. Now that we've discussed what it is and like a little bit of like an example of it, let's talk about when we can use it. I just definitely this part of it will be like a little bit tricky, but according to me and what I've seen at many places, it just feels like any problem that asks you to do like to find like a minimum or like a maximum, or like, you know, like you sort of see that at every step you have to like, oh, okay, I have to do this, and then continue until you reach the end, and then you're like, okay, this what I've done so far will help lead me to the final solution. I feel like those places, you know, you could use it. And also like if we have like some kinds of ways where I think I need to change it to mean that if you have like, if your current choice depends on future choices or something like that, or future sub-problem answers, it's not going to be possible. Greedy chooses first and then continues. So like that kind of thing where you just sort of, you know, let's depend on future choices, or like any kind of, it sometimes depends on past choices, but mostly it will just choose and then go. So that's greedy, because we're greedy about, you know, whatever we see best before our eyes, we pick it and then we continue. So yeah, so like I think in those cases it may not be the best. And then like also in like I mentioned with like revisiting some kinds of paths that you've already taken before, like with backtracking, you have you probably you're at a point, you have multiple decisions to take, and then based on like you just choose a path to go across, and then you later on you realize that that path is not working, so you need to like come back to this point again and then take another decision, see how that goes basically, and then keep doing that until you reach the end. And this is mostly like path finding kinds of things, and then like uh stuff like that. I think that's also not a good place to use greedy algorithms. So yeah, these are primarily my like my takes on this. But yeah, and I just wanted to like check with you real quick. Is everybody doing okay so far? Ooh. Is everybody like following through so far? Are we okay? Awesome. Great. So let's quickly talk about the other thing that we like, that we want to talk about. So what do you think is the difference between dynamic programming and versus a greedy approach? If anybody comes up with anything, like just put it in the chat, and we can, yeah. It doesn't have to be like a full sentence or anything. If you, okay, let's start with this. Do you see the difference between the difference between greedy and dynamic programming approaches? Like, do you see like that there is a difference between the two? Just let me know in the chat and we can discuss a little bit on it. Yeah. Yeah. Okay. Loving the answers. Where did I write? Okay, so dynamic programming. Yeah. Awesome. I think that those are pretty much, you pretty much nailed it. So like when you're doing dynamic programming kind of problems, it's mostly like yeah, that is pretty cool. Like everybody, like it's awesome responses. Yeah. So like with dynamic programming, like at each, like we sort of like, it's sort of like we need to memorize, and like we need to we can't just take it and move. It's not that kind of an approach. It's mostly like, like we sort of figure out one thing, that thing will give the next thing the answer, and then so on and so on and so on. We can do bottom up, we can do like top down approaches, and with greedy, it's mostly like I said before. So there is a difference, and I'm so glad everybody's like explaining it much better than I did. So yeah, awesome stuff. Let's sort of go to some of the, like, I'm not going to explain these in detail, but I like each of this is like super important when you're doing yeah, when you're doing when you're trying to understand how greedy algorithms work, and like what are some sort of real world or like examples you see here and there, it's like a it's just like, you know, minimum spanning tree, like traveling salesman problem. And they also see this is where they solved that problem. It was supposed to be an NP hard, but they I think that came out some time ago, some months ago, I'm not sure, but like definitely make sure to like check these out. And you know, yeah, if you think of more, so if you think of more examples and stuff, mention it in the chat and we'll, yeah, we're all learning here, so awesome. With that, I am going to take a quick water break. So if you have any kinds of like questions and stuff, like please drop it in the chat. And yeah, and I hope you're all following through.
All right.
Could you?
While Chethana is taking a break, I'm gonna post the link. Sorry, what were you saying, Chethana?
Couldn't find a mute button, but like I was reading through Audrey's like chat message, and I was, yeah.
Okay. All right. So let me post the link to everybody. So like you can access the coding problem there. You can access like the solution there on the repo link. Just a quick reminder to fork it before you edit anything else. Well, I mean, you have to fork it for the website that we give it, like the link that we give it to you. So feel free to try it with you. Feel free to try it yourself as well. And I just also post the actual problem, the LeetCode as well. So if you don't have access on webpo, feel free to write it directly on the LeetCode as well if you have a LeetCode account. Yes. Yes.
Awesome,
yes.
awesome. So yeah, I think we can, if everybody's okay, give me a thumbs up. We can like in chat. Great. Awesome. So let's start looking at today's problem. Okay, it's called the jump game. It's one of those definitely one of those problems that we may have seen here and there, and you know, it just definitely within the problem, like you would know that there's some kind of underlying greedy approach that we can try out here. So let's talk about it a little bit. You're given an integer array nums. You are initially positioned at the array's first index, and each element in the array represents your maximum jump length at that position. Return true if you can reach the last index, or false otherwise. So basically, you're just you're given an array, integer array, nums, and each nums of I is the maximum number of position jumps you can make from that position. So if it's like if we have an array of, if we're initially positioned at the 0th index and the first element is 2, from the 0th index, the maximum you can jump is 2 places. So you can either travel to 1 or 2, like, so like you can move, you can jump by 2 indices. So where I is the index at each position and nums. Yeah, that's, yeah. Can you get to the end of the array by utilizing up to the maximum jump value at each position? Like, which means you can either take, if you can make 2 jumps, based on whichever, like from whichever index you're on, you can either make 1 or 2 jumps. You don't have to make, you don't have to jump by 2. You can either jump by 1 or you can jump by 2. So utmost is 2. So you can take anything that, if you have 3, you can do 1 jump, 2 jumps. It just depends. And in some cases, if you reach the, like, if you're at the end already, then you don't need to make any kind of jumps. You're already there at the end of the, like you're literally at the end, and you don't have to make any more jumps. And that's the solution. If you reach the end, that's it. You just return true and you're done. Okay. So let's now think about the different kinds of ways we can do it. Okay, so have some stuff written in here beforehand. Let me know if you can see it. This is like my previously executed stuff, but okay. Yeah, so yeah, you just if you, like, you're not, yeah, like I think I mentioned this. Yeah, so if you're already there, then you don't need to make any kind of jumps. You can just break from the loop or whichever solution you're trying out. Because if you reach the end, I mean, if you see that you're at the end of the array, the position you are at is the end of the array, I think that is the only place where you may not need to make any kind of jumps. Like any other place, if you're at any other point within the array, you will always think of moving further to the right, which is the end of the array. The only place where you stop, and even if you have jumps and stuff, you don't want to make any kind of jump, is the last position in the array, which is your, like, here where you should be, and you just return true. Okay, so now that we have our, like, we've defined what our problem is, let's look at some possible solutions to it. Number one, when you think of something like this, definitely, like, straight away in my head, what I thought was, okay, so for now we read the first, also, like, is my font too small? Like, is this font size okay? Give me a thumbs up if it's okay. Okay, cool. Awesome. Okay, now if you're looking at anything like this, like, if any of us, basically, we'll start by seeing, okay, so we can make 2 jumps from this position, so we can try with 1 jump and then 2 jumps, and then we can see if we reach the end, right? For this element alone, we have 2 decisions to make. Like, let's take the first, if we take the first jump one, maybe if we go to 3, right? If we take only 1 jump, we go to 3. Then we're still left with 3, like it's like a nested loop of another bunch of decisions, like 3 more decisions within this. So now what do we do, right? Like, we can either do, like, we can take the 3 jumps. If we take the 3 jumps, it's like 1, 2, 3. We reach the end, and this is true. But the weird thing is, like, to know that we're going to take the 3 jumps, we will visit, like, what do I do if I'm here, and if I take 1 jump, if I take 2 jumps, what happens? And even for that 1 jump, if you go to the, like, if you take 1 jump, you're here with 1, and then you're here with 1, and then you reach 4. Like, if you take, like, basically, I think you're sort of understanding the gist of this. So for every position we are at, we will sort of visit the entire, like, our space, like our array, by, like, we will look at every single jump value there up until which you can jump. and then we'll see if we can reach the end. And if any of it returns a true, we're just going to return a true. But then it will require a lot of because it's recursion. So if the second one, okay, if the second one was 2, yeah. So like if we do this, it's like, okay, we start here, we take 1, right? What is wrong with me? Okay. We take 1 and then we do this. So 1, 2, and then we can't even go beyond this. Like, oh, but here we can, right? If we did you mean change it to 2 like this? Because if you do this, you can do 1, like you can do 1 jump. If you do 1 jump, then you're here. There's only 1 choice to make here. Okay, so I think even in this case, you can reach the end, because you'd be here, and then you would see that you can jump by one, and then you reach the end. Unless I messed up understanding again. But yeah, so I think like index location 3. Is this what you meant? 0, 1, 2, 3. Okay, so in this case, let's see. So 2, right? If we're doing 2, how many steps are we taking? Let's take 1 to see what happens. Because we're taking 1, we see another. Ooh, I forgot what was here before. Ooh, was it a? Yeah, it was a 3. Okay, yeah. So thanks. So like now we see we have a 3, right? So we can, if we take a 3, it'll be like 1, 2, 3. If we take a 2, it'll be like 1, 2. But since we already take the 3, okay, I think I missed a chat message before that. But so like for this particular case, we can take 1, 2, or 3. Basically what I'm saying is we need to visit all of the different things. I think, Joanne, I feel like this is still going to give us a true, because it's an utmost situation, right? So if we take a 1 jump, I take another 1 jump here, and then I take, I don't know, like 1 more jump from here. There's still, let's change it to 1. Now from here, from here, there's another 1. So you will reach your, you will reach like your end of the array, and that's it. No worries. No, I think I probably missed something else later. Sorry about that. But yeah, I think like you're understanding right now that it's when you see the greedy approach for this, you're just gonna be like, oh my God, like that's literally how it was when I was first solving it. But yeah, so this is called backtracking, and because you're making decisions you're making decisions, and then you sometimes, this is like I'm just giving you like the most ideal kinds of situations. Let's do this, right? In this case, we're saying 2, right? If we're starting with 2, 1, 2, let's take both the steps. Okay, okay, if we take both the steps, we're not gonna progress beyond this, but you literally wasted you visited 1, 2. 2 steps. But in this case, it's fine. What if I took 1 step? Then I would have had to do like one step, and then, you know, 2 steps, and then 3 steps, like that. And how about 3 looks pretty easy for us to get to the solution. Let's do 2. But like when you reach the 0 or something, you would have done so many kinds of like traversals and internal like you would have processed a lot of decisions that you should not have, or you're just wasting time doing it. Yeah, so like it's the it's like at every point you don't have to pick that entire jump. You can take up to that jump. You don't have to, like, if there are 3 jumps, you can take 1 to 3. You can either take 1 jump, 2 jumps, 3 jumps, but you shouldn't go beyond the 3. So you know, like basically something like that. So now we're noticing that it's like super like prolonged and stuff. Like in this case, the time complexity is going to be exponential, and you basically, because this is like a recursive approach to solve the time complexity, there are different like methods that people use. They use substitution method. They use, what is that? Yeah, this you know, iteration method, and then there's something called master theorem, I think. But those are not like, you know, like what we sort of need to understand, that this is not going to work, and it's going to do it in exponential time, and we don't like that. And O of n, because like when you make recursive calls, you're sort of, when you look at this, right, it would be like a recursive call of 2, recursive call of 1. So you sort of need to find out what each of those answers are. So what happens if you take 1 jump? What happens if you take 2 jumps? And how is that going to, like, what sort of answer is that going to give for that 1 jump and 2 jump kinds of, like, you know, we need to find those answers, right? So for that, you need to look at the next, you need to process that. And when you process that, more things get added to that call stack. Shouldn't do this. This is the call stack. So as all of these recursive calls, you're gonna, it's going to call other recursive calls, and it's going to keep piling up in the call stack. And then like, and I think like, because it's just like a, to sort of find one, we need to find like overall within the length of the, like, and it has an upper bound of the length of the array. So you know, like, to sort of, as we evaluate, the call stack thing is pretty interesting, because like as you evaluate each of those, basically each of those calls, it gets popped out, and as you like, it gets popped out until you hit the stack capacity, or like, not the capacity, sorry, your stack is empty, your call stack is empty. So too much of talking for just that space thing, but yeah, that's one. We're not going to do that, but can we do better? Like, definitely, if you see any kind of like recursive solution, or like a very, very like you're seeing that it's wasting cycles and stuff, then you would definitely have a dynamic programming approach to it, and what is memorization and stuff. We'll talk about it in a second. So if you see that, if you sort of, you can always get to like, it's mostly like, can you get to this position from where you are? Yes, because that's the first position you're at. So you can start with true for that. Can you get to this one? You have to evaluate that. And when you evaluate that, this this will become true as well. And then when you go to like any kinds of decisions after that, now I've changed it to this, but let's just put it to, I don't know, 1, 1. But as you go on, if you notice that, you know, like, can you get to this from where you are at? Suppose you're here, and then like, can you get to this? Can you get to this? You sort of do like as you figure out if you can get to some kind of like some kind of position within the array, you sort of mark it in your DP array. I'm definitely not doing justice to this just by talking and stuff. So I definitely encourage you to like look it up within the solution, or like post it in the channel so somebody can get to it. And yeah, so what I've written here is basically that. So if we mark the ones we visit from that particular index, we don't have to visit those again. Like if you have to like backtrack or something like that, you're like, okay, this doesn't work. If you go all the way with, like, suppose you take one step and then you do one step, but you should have taken 2 steps. So like when you hit that, oh no, I can't do it, you sort of like, when you hit that point where you're like, okay, I'm not able to reach the end of this, so let's go back and let's try another bunch of steps, like another jump value or something like that. Let's see how that turns out, and so on and so forth. So if you get to that, like when you backtrack, you're like, oh, okay, like we already have this thing, this DP array that sort of stores if we are able to get to this one, like if we're able to get to this particular position before. And like I think I'm missing a key piece there, wondering what it is, but yeah, like because our primary goal here is to just break down the other approaches a little bit and then talk about the greedy one more. I'm just gonna leave it at that. But memoization is basically like, and also we would have like a visited set, like like if you've already, I think if you've already seen something, you'll store it in that set, and then like when you get to that set, you would sort of look up based on that set within the DP array, and so on and so forth. But at the end, you will return, this one will either be like a true or a false, because this is the last cell is literally your answer. Like, like you can either get to it or not, because we set everything to false initially. If you don't change it to true later, you're just going to return the false. So you just return the last cell and then be done with it. Okay, so time complexity. For basically, this is like a since we're doing like a for this particular one, you would basically look at every other, like how do I say this, for the index we're currently on, you'll sort of look at every other index that comes after it. Can you reach this? Can you reach this? And like it's definitely like super involved, and like this needs its own kind of session. But yeah, so because we're doing like, it's still not doing fine in terms of time for the optimal solution. So I've written this down, and this is based on a solution from before. So let's sort of discard all of this in our head. We know that backtracking, dynamic programming are not going to work. So why is dynamic programming not going to work, right? Like you mostly assume that like most of the times it works, but the greedy solution to this is a one pass over the entire like your input. So like, I am sorry, but like things like this did not come up to me like in an interview. Like I'm not going to be like, oh God, like, we're all mostly going to be doing like long-winded stuff, and then somebody's going to tell us, oh, maybe you can do it this way, and then we'll change it. But let's look at our greedy approach here. So I've tried my best to sort of prove why the solution works, but like I think I'm going to talk about the solution a little bit, and then I'm going to talk about the two properties that I've mentioned to prove that solution. So basically, I can't stop smiling because I'm thinking of the solution. I'm like, what? how, and yeah. So basically, given your array, if you just go to like the last, if you just traverse from the end to the starting, and at every turn you sort of have to keep track of something called like what is the last good index that you're supposed that you can reach from here, and like what is like, what is the best how do you, how do I say this? Okay, so if you're at this current position, like how do you reach from here to the last good index? The last good index is mostly like the position right after it. So like how do you reach from if you're, suppose you're starting here. I'm not going to be starting here because this is the optimal, like this is where we should be. So if we're starting from here, let's think about it going backwards, right? So can we get from here to here? One jump, right? And basically it's like the current index we're on plus the jump we're allowed to make. So the current index is like, I should have written that down. Okay, I'm gonna write it down now. What is up with me? Let me just write it down separately, or like, it's fine. 1, 2, 3, 4. I'm really sorry, my typing skills aren't the best in general. Okay, so we're in this, we're at this third index, and then this is the fourth index. The fourth index is our destination index and our last position within the array. So if we reach that, we can assume that that's it, like you've reached the end, and that's what your question wants you to do. So you're starting from the second last position in the array because the last position is where we should be. So from here, can you get to here? It's just one jump. You're seeing that you have one jump. Yes, you can. So this part is done. So like this particular sub problem of where you're looking at, can you get from here to here? You're able to get from here to here. And so what would you do next? Because we're doing like a reversal or like a, traversing backwards. The next step, you just move here, but then you would also move. Okay. But then you would also move your, this is the last good index that you wanted before. Now you would move it one step, like you would move it to where I was. Like I is this pointer that we're continuously using to travel backwards. So basically, if you will take, I mean, then the next step, this is going to be like your 3 is going to be like your good index, and then you'll see, okay, from here, can you reach here? Okay, yes, you can, one step, and then you can reach there. Okay, and then you'll sort of move your I index again, which is now at 1, and then your last good index, because you can see that you're able to every time if you see that your current index that you're on plus the jump length that you're allowed, if it is sort of greater than equal to your last good index, then that means you can make that jump, or you're good to go and you can just move on to the next. Then you can just update the last good index to I and then continue. Let me do one more, and I mean, let me go through this entire thing once more. So yeah, so like let's have the last good index over here as a variable so that we can actually see what's happening. And remove this. sometimes have difficulties moving with pointers, which I shouldn't, but yeah. Our last good index, initially we'll assign it to like your last index of the array. So that's going to be like your length of nums minus 1. Now we're here, right? So what we're going to do is at every step along the way, what did we want to check? We wanted to check if our I, the index that we're on, plus nums of I, if it is equal to, like if it is greater than or equal to our last good index, then that means we can reach this last good index, right? Like, because we, from the index, why are we looking at the index we're on? That's because it's like, so if we're on 3, there should have been some other kinds of jumps before that got us to 3. And you know, like if this is 3 here, it should have been some other, we should have taken 3 jumps from somewhere else to get to this index 3, or maybe 1 jump, or maybe 2 jumps, but doesn't matter, we're on 3 right now. And we got here, right? Like, since we're doing it from the end to the start, let's continue like this. So if we're seeing that we're able to reach this, like this last good index here is 4, from 3 to 4, are you able to reach it? Then what we do is, within the same iteration, you sort of set the last good index to your I, which means your last good index will be 3. We'll walk through it to see like why this works, like, you know, yeah. So now our last good index is 3, and then we're at the next iteration. So let's, yeah. Okay. So we're currently here now. And our I is 2, our nums of I is 1, and last good index is 3. So can we get from, like, are we able to get from where we are at I, like, you know, like get from I to this, and I plus that value at I, so 2 plus 1, 3, right? So is 3 greater than or equal to 1? I mean, 3 greater than or equal to 3? Yes, it is. So this means that we can sort of move our last index over to 2. Okay. So, and then I also moves to, you know, it also moves to the previous one, reversal, like, yeah. So again, now we're again at that same place, and we're like, okay, now I need to check if my current index plus the value that I have here, if it is greater than or equal to the last good index. Can we get to the last good index based on the jumps we have and from the position we're at? So this one is, what is it, 3 plus 1, right? 3 plus 1, and our last good index is 2. 3 plus 1 is definitely greater than or equal to 2. So so then what we do now is, again, we change our last good index to 1. Okay, that's done. And now we move our I to 0, right? And at this point, what do we do? I is 0, 0 plus 0 plus nums of I is 2. So 2 is 2 lesser than or like is 2 greater than or equal to your last good index, which is 1. So yes, it is greater than or equal to it. So then we sort of move our last good index to 0, and this one sort of like stops, the loop stops. And then at the end, like, what do we do to check? We check if the last good index equals 0 or not. If it's equal to 0, like, yeah, you know, then we reach the end of it. If it's not equal to 0, then we hit a snag somewhere else, or like we sort of missed in this condition to, you know, the ideal case is every single time the last good index will move by one, like it will move, yeah, it would sort of move by one, or like it would sort of move iteratively, gradually decrease until it gets to 0. And then once we break out of the loop, that should be, that should be the case. Like we just return it. I should have put in negative scenarios to see if we hit a snag. Could I get a couple of negative scenarios in the chat? The code is super, like, you can see literally that it's not that involved or anything, but the concept is definitely, I personally, I would not get this intuition in one of those high pressure situations, but it's good to know that there are like approaches like this. And if you see, like, you didn't really need to do any of those things from here. Like you didn't need to look at all of the decisions and stuff like that, right? So yeah, so like, like, I think, let me just go through this as well. So because we talk about like greedy choice and like, because those two are the key ingredients to make up your greedy algorithm. To the best of my knowledge, I think the greedy choice we're making here is, every single time we're saying, okay, can I get from here to the next one? Can I get from here? It shouldn't be I+1. It should be the last good index. Oh, I've written that. But this is an ideal case. Maybe that's why I've written it. So if you see, can you get from, So can you get from, if you're, okay. Yeah, I think in that case, you just basically, because you, I think you just return. So our last good index here would be just this, right? It would be 0. And then your I would also be 0. And your, yeah, okay. So very good. Like I'm sort of thinking what we need to do here. So if our, okay, so we're starting from the end, which means this will already be at 0, and then our I will also be here. And if you do I plus nums of I, like it's still going to be 0. Is 0 greater than or equal to your last good index? Like it is equal to it. But then, like, yeah, I think in this case, it's just you just, because you're already there at the last index, I think you just return true, right? Does that make sense? Because, yeah. So it works. And yeah, so what I was saying is, like, if you, because you're doing all of these, like, you're just saying, okay, can I get from I to the last good index based on my jump value at that particular index? If I can, then that means I'm, updating my last good index. It means that I can solve that subproblem, and I'm able to get to that last good index position, right? So in that case, then I'm just gonna like make that greedy choice and then continue. What is my greedy choice? I'm thinking it's to, every single time when you can make that jump, you're just, moving your last good index, assuming that you can reach, suppose if your last good index was here, right? If it was here, then you're just basically, everything that comes after that, you're just able to reach it. And like, with the particular I and the nums of I, you're just going to check if, you're able to reach that particular point. You just, if you If you can, then you're just going to update the last good index and then you're going to move on. That's it. You're not going to look at anything else. So in some kinds of ways, I think because you're just moving to the next iteration and stuff, that would be like your greedy choice. And your optimal substructure, if we saw before, if you remember from before, it's like, suppose like, we know that since we're here, then we've sort of solved this optimally, and we've sort of solved this optimally, and sorry about that. So at every turn, we're like, we sort of know that we're getting to the next solution, we're getting to the next position and stuff like that in an optimal way. This is the optimal way because we sort of decided to start traversing from the end, and then do this kind of approach. So I think it sort of does sort of like, if you can finish this problem optimally, this and this and this, everything else at the end, you're just going to assume that this works, that's it. So I think this also exhibits the optimal substructure property. These two are like completely like what I think. So there may be like cases where I may be wrong or something like that. So like, just definitely like, if you think doesn't make sense, let me know. And yeah, I think with that, let's talk about these at the end, because like this problem, the solution is such a treat. I swear, like, yeah. So if you think we can start with the coding, give me a thumbs up. Yeah, I think you can do it forward too, but then this one seemed to be super, like, for some reason, it just, the intuition is a bit like, why are you doing it that way? That kind of a thing. So yeah, let's talk about, let's do this. It's just 4 lines of code. Again, the code is not any time actually with every kind of problem. The code would be super straightforward. If you had like 2 minutes to do it, you can do it. Okay, hope I don't mess this up. So let's first start off. What are we going to do? We're going to initialize our last good index. Because we're going to start from the end, let's set it to the end. Length of nums -1, which means you will exactly do length of nums here is like 5 - 1, 4. Sorry, 5 - 4, 1. 5 - 1, 4. Oh, okay. So now what are we doing? We're traversing from the end, right? So for I in range, length of nums minus, I'm going to say 2. I'm going to say 2 because we can just start from here. Like we could start from here too, but like, it's fine. Like, why do we don't need to, if we just know our last good index is going to be here, like at the end, right? And the end is where we want to be. So let's just start from here. Can you get from here to here? Get from this position to this position based on based on your jump value, I guess. So -1, -1, y -1, you're traversing backwards. And for this, we're basically going to, take care of that condition we talked about. So if I plus nums of I is greater than or equal to our last good index, then we set our last good index to, we set it to I, and then the loop will take care of the rest. And at the end, we just have to make sure that our last good index equals 0. If it doesn't equal 0, then some other weird stuff somewhere. But last good index equals 0. That's about it. Like with the coding like portion of it. Okay, let's actually plug this in to see if the solution takes it. But let me go back here. Just added in some boilerplate stuff. Jump game is our object, and then can, what was that? What was my name? Okay, what's my method's name? Can jump to, and let's see if it works. Hopefully it does. What did I do? Where did I miss that? Can jump to, oh, okay, thank you. Oh, okay, let me find this thing. I'm not sure what I'm doing. Okay, 3, 0, 8, 2, 0. I'm so sorry, it's taking a long time again. Okay. Let's just stop being too nitty-gritty about this. Let's try. So like what should be the output of this, right? So 3, if you take 3, it's maybe that should be a true. Okay, let's just see if it works. Yeah, it seems to have worked there. So I think if we do like another, yeah, if we do like another breakdown, there are so many solutions like to the same problem, but I'm sure the backtracking one and like all of those other ones, they're going to do a time limit exceeded on LeetCode because that they don't like it for some, like, yeah. So yeah, that's sort of it for the coding portion of this. Let's just jump back to the slides and talk about next steps for like 2 minutes, and then yeah. So best time to buy and sell stock, very popular. It's an easy problem, and it's like you're given an integer. Actually, basically what it is you're given an array of prices, and each at each index, at each I, you know, like within prices, it has like a price, or like, yeah, it has a price. Yeah. So basically you have to maximize, you have to return the maximum profit you can achieve, like you need to buy and then sell. Like you need to buy a stock at some point in the days, like each index I is going to be the day. So basically it's like you shouldn't do like multiple transactions or anything. You just have to do one transaction. I think the multiple one is a variation of this. I'm not sure, but definitely look at this and see if you can sort of like figure it out. And meeting rooms too is like, it's like any kind of like course scheduling, like, you know, interval scheduling, like jump game, and like there's that other like frog, like there would be like a frog and it has to reach the end, and there are like 3 lanes, and then you have to, there are like obstacles within the lane, you have to reach the end, like in some kind of I think you're limited by some factor. I'm sure about it, but I forgot what it was. Sorry about that. But you can definitely like check these problems out as well.